بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is a lecture on Introduction to Retrieval-Augmented Generation, and this technology represents one of the important trends in generative AI and large language models because it helps reducing the well-known issue of traditional large language models related to hallucinations. Okay, so I'm going to provide you an introduction to this concept, and also we will do some practical activities on how we can build a chatbot for Al Faisal University, okay, that can understand any context related to Al Faisal University and respond to any kind of questions, as opposed to, for example, if we go to ChatGPT or other language models, we ask very specific questions about Al Faisal University. Most likely, we might not have the correct answers because of the lack of the training data and the possible hallucination that we can have. But with the Retrieval-Augmented Generation, you will observe that we can reduce the issue of hallucination to almost having an accuracy close to 100%, because we will be able to retrieve the required context for very specific tasks like the chatbot that we want to develop, and make the large language model much better and much more reliable. Okay, so what is wrong with old language models like ChatGPT, for example, or GPT by itself? So as you already know, when we want to build a large language model, we start with making a pre-trained model. And the pre-trained model, we will take a large corpus of data that we will use to teach the language model the language capabilities and how to complete sentences. Okay, it's basically a completion model. And then we can do a fine-tuning in order to provide the model with instructions, the ability to execute instructions like responding to questions or summarizing text or other type of tasks depending on the objective. And the problem here with when we rely solely on pre-trained knowledge, first of all, this pre-trained model will have only static knowledge. They will be able to provide you answers or completions only based on the data they have trained on. But every day we have new type of data, okay, in any context. So the language models are not able to provide you accurate or reliable responses related to new information. For example, I remember when I asked ChatGPT 3.5 at the early days who won the World Cup, so he was referring back into 2018, okay, because it was not trained on 2022 during the Qatar World Cup, so it doesn't know about this because the information that it uses to respond to the questions were static, okay, and is not up to date. So this is one of the issues, and also the lack access to real-time, private, and domain-specific information. Large language models don't have access natively to real-time information. Now everything, there are new news. Now if I ask a language model about the news of today, it's not able to respond. It was not part of its training data. Or I want to ask about domain-specific information. Like, for example, very specific questions, I don't know, about domains that it was not trained on, it will not be able to respond. And this makes it prone to hallucinations, al-halwasa, because it's not able to respond correctly to dynamic information or real-time data that is happening and that was not part of its training data sets. And to overcome this issue, we have recourse to the Retrieval-Augmented Generation, which basically the concept is very simple. Instead of relying on the language model as a knowledge base, we're going to augment its knowledge base with external sources. Okay, مثلا نقول له search over the internet this information, or we provide some kind of context to the language model to use it as an external source of information, and we will leverage the reasoning capabilities of the language model to provide answers based on the query, the questions, and also the context that we will provide it to respond to the questions. Okay, so one of the early approaches after pre-trained models, as already mentioned, is to fine-tune a model over a set of labeled corpus on very specific tasks, like question answering, as already mentioned, or writing coding programs, or for example, summarizing text or doing machine translation. So this is what we call fine-tuning. You already know about the fine-tuning process. And again, this can help augment the knowledge with the new data of the pre-trained model, but this knowledge will remain still static. I mean, once you make a fine-tuned model, this knowledge is not going to be updated. So after 2-3 days, 1 month, or a couple of months, the knowledge that we were fine-tuned the model with will be also updated, and it will be unable to incorporate new type of information. Another thing is that now if I have a new type of information, I would like to fine-tune again the model. That's possible, but this will induce a higher cost, because now there is a computing cost, or if you subscribe to an online APIs like OpenAI, if you want to fine-tune an OpenAI model, there is an induced cost. You need to pay money in order to fine-tune the model with dynamic data or new type of data. So another big issue also with fine-tuning language models. Now imagine that you fine-tune the model. Let's say you take a GPT, you fine-tune a model with Al Faisal University corpus, and after some time there are some changes. Some people left, some people came, the program have changed. So your pre-trained model will become obsolete. So you will bring a new data and you will train again. So there is a high risk that when you train on a new data, it will forget some part of the data that you have used in the first pre-training. This is what we call catastrophic forgetting. So it's like we as a human. Now, when you focus on very specific thing, you might forget other things that you have learned in the past. Okay, same thing, the language model may forget some of the important details that it knows before because of the fine-tuning process. Because what it will do, the fine-tuning, it will change the weight of the model. And the change of the model may impact the capability of the language model to remember some of the facts of the previous model that was fine-tuned. Okay, so domain-specific training may erase or drop general knowledge that the model has to know before. So all of this, they make from fine-tuning of language modeling just a partial solution. Okay, it's not very convenient to very dynamic type of data because training has a cost. It will take time. Deploying new models also is not easy. So we will fine-tune models only when we have some kind of very domain-specific task that doesn't change very often. That could be a solution. But in the long run, still, fine-tuned model can also lead to hallucination. Let me give you an example. So this is an example of a model that we have fine-tuned in the past. And I provided some information about myself in this model. But look now, I asked this model about help answer questions, providing informative and accurate responses. This is the system prompt. And I asked about myself. So this model that was fine-tuned just provided some kind of hallucinations. There are some information that are correct. For example, academic known Tunisian, this is correct for his contribution in the field of robotic and automation. The first sentence is correct. But look at the second sentence. He holds a PhD in system engineering. This is not correct. From National School of Engineering, this is not correct. And so there is a combination of correct information and wrong information. This is due to catastrophic forgetting. Not the fine-tuning model was not very doesn't have sufficient data to provide correct answers and so on. So there are limitations for fine-tuning models, as you can see. Now, if I want to make sure to have correct information, I need to provide the correct context for any question. You know, the optimal way is that when I ask a question, I will try to bring the correct context that contains a response. I will retrieve factual information, and then I will append the query with the factual information, send everything to the large language model, and then this helps the large language model to get the right answer, and then we will use the language model to generate the answer, to write the answer according to specific system instructions or system prompt. So in this case, we will rely less on the language model as a knowledge base, and we will rely more on the language model as a reasoning model. Okay, reasoning model that can understand the query, the possible answers, and then formulate an answer. So this is pretty much simple when we say retrieval-augmented generation. This is pretty much similar to the context of open book exams. Now imagine that you do an exam that is closed book. You will rely on your specific knowledge. You may forget some information. Okay, so in this case, your likelihood of correct answer may be less than if you have the textbook open. You can retrieve. For example, you have a question in the exam, you go to the textbook, go to the right page, read the answer, and then you will write the answer yourself. This is exactly what happens in retrieval-augmented generation. Okay, it's like an open book exam. You bring all your resources. Whenever there is a question, you will not rely on your specific knowledge. You might have the correct answer, but you say, okay, let me have a look. Maybe I missed something. Okay, and in this case, you will bring the right information, and then your work or your duty or your task will be just to generate the answer, to write the answer based on your understanding about the question and the information that you collected from the textbook. Does it make sense? So if you understand this, this is the main concept of the retrieval-augmented generation. So at the end, what is a RAG? A RAG, it's a hybrid architecture that combines document retrieval. So the first task in the RAG is to retrieve the correct documents that are related to the question. Okay, that combine retrieval with generative AI. When we say generative AI, it means the large language model. So the large language model, before it generates any answer, it will get a support from a retrieval system to check the query, find the right answer, and then send both the context and the query to the generative AI model to generate the answer. Okay, this is how it works. And the retrieval will bring external, up-to-date knowledge generation, and the generative AI will craft a natural response. Yes?
So the element here will only do the
Generation, yes.
Understanding will be done by the RAG?
Yes, the RAG is the whole system. So what it will do, it will take the query, find the most likely answers. Okay, for example, now you ask about, give me the phone number of the dean of the college. You might not remember this. Maybe you have it somewhere, but you forget about it. So you'll go to the repository. So now the large language model is going to go, for example, to the website of Al Faisal University, going for the College of Engineering, looking for the phone. So it will search with keywords. It's like you do in Google. Okay? Or we'll search using semantic similarity, using vector store. This is what we are going to introduce today. So there are different ways on how we can access external knowledge. It can be internet search. It can be semantic similarity with a vector store, as we're going to introduce it today. It can be also fetching an API. I would like to know what is the temperature now in Riyadh. I will ask ChatGPT, for example. It will invoke an API about the weather, sending, I want the weather information about Riyadh at this time, getting the answer, sending both the query and the response that it gets from the API to the large language model, and the large language model will understand both the query and the response, and then generate the answer. Okay, this is how it works.
Can we say that when OpenAI introduced web search, they use some sort of RAG?
Yeah. I mean, these tools, it's an enabling technology for retrieval-augmented generation. Okay, so the most common practice is to use a local vector store, but any kind of external tool, it's based on external up-to-date knowledge. It can be a database. Okay, I can fetch a database. So one of the chatbots that I have built in the past was for a real estate company. They wanted just to make a chatbot when you want to look for any apartment. You just write your query in natural language. This query is going to be converted into an SQL query. We bring the information from the database. We put both the retrieved rows from the database with the query we send to the large language model, and then we have a very nice answer according to the system prompt. That's also an example of RAG. So we can fetch a database. We can fetch a local file. We can fetch an API. We can search over the internet. We can fetch Google Drive, Dropbox, any kind of available external sources. Social networks, you can think about plenty of external sources now, and there are tools that we can bind to a large language model in order to have this accessibility to external data. Okay? That's good. Okay, so this will help to boost the accuracy, the relevance of the responses, and provide a factual grounding in AI answer. So this dramatically reduce the issue of hallucination. But the most important part is actually the retrieval. Okay, now when you do RAG, for example, you have any project when you will do RAG, probably now in the second phase of this course project and Dr. Ridal project as well, you will do a chatbot. And this chatbot should not be just invoking an LLM, because this is not going to be an added value. So you need to bring an external source and make some kind of retrieval. So this is the biggest milestone that you need to focus on, is to make the best retrieval model. Because if you don't bring the correct information, so the large language model will have misleading information. So this is not going to help the language model to generate the correct answer. So yes.
We have to think about understanding the context.
Exactly, yes. You need to understand the context. And there are ways. Okay, so the object of the retrieval is to find the relevant document. And then, of course, the document is the set of data that you will put or that you will attach or bind to the large language model. It's the relevant information that is collected. And then both the query and will be sent to the large language model to generate the answer. And finally, you will get the answer. And this is the workflow. So as a user, you will ask a question. So this is your query. It will go to a search engine, which is our retrieval. Okay, here, if you have local information, you can do semantic search. You can also browse the internet. In any case, you have several sources of data. It can be, so basically it can be text, but it can be also videos. It can be pictures. It can be any kind of data. All is based on embedding. So there is one nice course in deeplearning.ai if you are interested. It's called Chat with Your Video. Okay, it's RAG on video systems. And the idea is simple, We just make an embedding model for the frames, embedding model for the caption. We put everything into a vector store, and still cosine similarity to map the query to the source of data, the retrieval system, as I'm going to explain. Okay, so now we find the context for the answer using semantic similarity, and then we will append the query of the user plus the context that is found, send everything to the LLM. Look, now at this stage, the LLM doesn't need to rely on its own information because it has the question and it has a context to respond to this question. So it will be biased by the context. This is why it's important to have an efficient and reliable retrieval system, because the context will guide the response. Okay, and we know that the LLM is good actually in understanding what's going on, and then based on this it can generate an answer, and this answer will go back to the end user. So yeah, this is the big picture. Again, you have a user generates a query. Now you have a knowledge base. You will make a search. This search, you can think about it as an internet search, fetching a database, fetching a vector store, fetching an API. You can think about different type of tools that will allow you to access external sources. Now let's make an abstraction. You just search an external source regardless what is this source, and then this will provide you relevant documents that are related to the query. What does it mean related? Here, if we use, for example, vector store, we're going to use semantic similarity. We have a vector that represents a query and a vector that represents a document. We do the cosine similarity. We will have a similarity search, and then they will be ranked. For example, I want the top 3 or the top 5. We will rank them according to the similarity search score, and then we choose these relevant documents, and then we append these documents to the query, sending to the pre-trained large language models or to the instruction fine-tuned model, and finally we generate the answer to the end user.
Let's say that we're going to build a chatbot for Faisal University and we have provided the Faisal website. that it's usually updated.
Yes.
So whenever there are changes in the faculty or whatever, so we do not need to monitor the system because it's already we have inserted the website. Is that right?
Yes. Now, if you rely on the website and the website is up to date, you don't need to make much changes. In any case, you don't need to train anything. So this language model, you don't need to train it when there is new data. Now, imagine that your data is stored locally. What you can do, remove the old documents and bring the new documents, vectorize them, and that's it. It takes just a few seconds to do that. Okay, doesn't take long. It's not like fine-tuning a language model again and again. It will take several hours and it will induce a cost. And you need to provide a labeled data set with questions and answers. I did this, for example, in Princeton University. The first chatbot that we have built is called PSUGPT at that time. We fine-tuned the model using 33,000 questions and answers. So a huge number. And at the end, the accuracy was good, but you know, it's not always 100%. I mean, sometimes if I ask about, give me the course code of programming 2, for example, it can make mistakes because it's fine-tuned, but still, you know, it's prone to errors. There are some hallucinations. And now after a couple of months, many things changed. The chatbot becomes obsolete. So if I wanted to make it up to date, I need to train it again. But this is not useful. Now, when we use RAG, it becomes piece of cake. You know, it just takes 5 minutes to update the chatbot and keep it up and running. So this is why RAG, if you go to the industry, if you want to make a chatbot, it's basically RAG. And beyond the RAG, there is now the agents that are more sophisticated. Okay, agents, they can do complex tasks. Now, the RAG can help you fetch data, but if you put RAG inside an agent, you can do more advanced and iterative operations just based on a single query. Okay, so under the hood, the RAG system has 3 main components, which is a generator, which is our large language model. This is our AI model. And the knowledge base that we will bring, it means the external sources that we will put available for the large language model, which is an indexed external data, can be PDF, websites, but it has to be indexed or vectorized. And also the retriever, which is a system or a tool that will help finding the relevant documents. There are different things, like for example, BM25 or TF-IDF, or using cosine similarity for retrieving the documents.
Doctor, it's usually ranking models and retrieval?
Yes. So the basic work of retrieval, I'm going to explain this, is the knowledge base is basically, if we consider local storage of these documents, we will vectorize them. So it's a database of vectors. And this is what we call a vector store. So, and then when you have a query, we also convert it into an embedding model. So the vector store will convert any document to vector using one embedding model, مثل OpenAI, text small 3 or something like this. And then any query will be also converted to a vector, and then we make the cosine similarity between the query and all the documents into the vector store. And the dot product is very fast. I mean, if you have thousands of documents, you can quickly have a score index of the query with all of these documents. And at the end, you can select the top 3, the top 5, depending on the context that you want to have. And then you will send everything to the generator. Okay, so the retrieved text are injected as a context into the generator to guide the response. But of course, you know, sometimes the retrieval or cosine similarity might not be efficient. Sometimes you have long documents with a small query, so it can be confusing. There are some techniques like re-ranking systems. So there are some techniques that can understand all the contexts that are retrieved and then re-rank them according to the relevance. There are many parameters that guide the performance of retrieval-augmented generations. And so the retrieval step, as already explained, it's based on converting text to embedding, as we have already introduced previously in the course. You convert queries, documents into a dense embedding. You can choose any embedding model that you want, okay, and use it as a reference to convert your queries or documents and save them locally into a database that we call a vector store. And we can find the relevant documents by measuring the similarity using the cosine similarity between the vectors stored in the vector store. And finally, we return the top K most relevant documents. And these documents must be stored into vector stores, as already mentioned. There are like Face, Chroma, and other technologies that are used to store these documents. Okay, so these are the generation step. You will start with an input query, and this query will be merged with the top K documents and will be combined into a single context. And this is going to be sent to the large language model to generate answer conditioned on this context. So the large language model will not have the freedom to generate any answer. This answer will be strictly guided by the context, of course, and based on the level of understanding of the large language model, you know, this will also impact the quality of generation. The quality of generation is depending on the quality of the language model, depending on the quality of the retrieval, but mostly the quality of the retrieval is the most critical. And I have a recent research paper, maybe we will post it soon in ArchiveX. It evaluates the performance of retrieval-augmented generation under different hyperparameters. So I can share this with you to have more understanding about the impact of the parameters. So the fine-tuned output. So the output can be fine-tuned for very specific use cases. And this is an example. For example, you say, what's the capital of Brazil? We will look for many documents, and then one of the documents probably will have Brazil is the capital is Brasilia. And finally, I will send a query, press this context, so that the large language model will generate the capital of Brazil is Brasilia. Okay, and okay, so why do we use RAG, and what are the benefits of using RAG? First of all, you will be able to maintain easily an up-to-date knowledge. You don't need to train your model very often, okay? And no more outdated responses. Whenever you have any type of new data, you can just add it to your documents, you can vectorize it, and your chatbot or your retrieval-augmented generation system will remain up to date. And this will help to reduce dramatically the impact of hallucinations that we can observe on large language models. So you will have ground answers because you will append a context to the query. So you will precisely guide the large language model to provide you an accurate and reliable answer. Another advantage, it has a domain flexibility because it can work with any custom data source. Okay, it can be a text, it can be a PDF, it can be Word documents, everything that could be vectorized. It can be multimodal as well, like videos, speech, for example, or images, anything that can go under an embedding model. So we can easily store it as a knowledge base in a vectorized database. And it's scalable, okay? You can update the knowledge base without retraining the model. Okay, despite the advantages and benefits of retrieval-augmented generation, there are also some challenges that we need to be aware of and some limitations. So first of all, the retrieval quality, as already mentioned, that plays an important role, okay? So if you have garbage in, it means if the retrieved documents are garbage, the large language model is going also to produce a garbage. So this is why it's important to make sure on how to make your retrieval the best possible. And there are different strategies that starts even how we can chunk documents or divide documents into different chunks that contain meaningful information that will help providing the right context related to every query. There is also a challenge of latency and cost. So when you use retrieval-augmented generation, before starting generation, you need to retrieve documents. And this, in some case, especially if your knowledge base is very huge or is an external source that is located through the internet, this can induce more delays. Okay, especially now in chatbots, you want to have a very quick answer. So that could be also an issue, and also it will induce a cost, either a computing cost, a memory cost, because the vector database can go up to gigabytes of data depending on the scale of your data, and this can induce to have slower performance than LLM only, because we have two steps instead of only one. But there are some ways on how we can mitigate the latency challenge. So another issue is the input size limit. Imagine that you have a long document. Now we have the ability to plug a large context into a large language model. But initially, if you remember GPT 3.5, it didn't accept a context more than 8,000 tokens or 4,000 tokens. So for example, if you retrieve a lot of documents, and these documents are huge, you cannot send all of them with a query to the large language model because the context or the window size of the language model is small. But now, yesterday Lama asking questions about research papers, we need to provide these context, and fact checking, real-time fact checkers. So all of these are possible applications. So the future direction now is to use multimodal RAG, text and images. There is a nice course that I've taken on deep learning.ai. I already mentioned this. I really recommend you to take it. It's not difficult. Provide you a practical way on how you can make a chatbot with a video. And what is the principle? The principle is simple. Now, in this type of text-based chatbot, we are going to vectorize text, and then the query will be a vector, the text will be a vector. We do similarity search, and then so same thing. We will have to vectorize both. For every picture in the video, we will have a caption, and this caption will be vectorized, and the frame of the image will be vectorized. So whenever you ask a question, we will search the most related caption to this question, and this will help me to find the corresponding picture, okay, to this particular query. And we can also embed images. For example, I can provide a picture and say, provide me the closest picture in the video, and this can be used, for example, in surveillance system. Especially, imagine that you look for a person in a video from surveillance. Maybe you can provide the picture of the person, and then we look which frame that contains the most likely picture of that person. Yes. Yes, but here it's possible. We can still embed the voice, okay? But here in the course that I talked about, they embed pictures and their captions. But of course, when you retrieve the caption, you can replay the portion of the video because this video will be tagged. So you can replay it again, from that position when you search. For example, can you replay 2 seconds or 3 seconds depending on.
For the picturization, it will be huge,
Hmm?
right? For the pictures that we will bring on the-
Yes, of course, you will have another dimension, okay, another dimension for the pictures. So maybe it will be doubled. So there are embedding models that have the ability to embed both text and images. And this model was proposed by Intel. It's called Tower Bridge or something like this. They have trained this model to embed images and their corresponding captions. Okay, and now this is a trend. Multimodal is not only text and images but also voice. And OpenAI recently, it's not recent, quite a couple of months ago, but now there is the real-time API in OpenAI, which is a speech-to-speech. It's no longer, because before, when you want to make a chatbot with a voice, you start speaking, you convert this speech into text, and then you send text to the large language model, will process it, bring back the text, then you use a TTS to convert it, and then send back the speech to, and this takes time. Even if you do streaming, it will take 2 seconds to respond. But we as human beings, we usually require 200 milliseconds to start a response after stop talking. So they made an API that is speech to speech. You talk, it will not be converted to any text, and then it will send you back a speech right away in any language. It's pretty much amazing, quite fast, almost instantly when you stop speaking. And this is the same thing that you can find if you have ChatGPT on your mobile device. They have this speech. It's basically used the same real-time API. Okay, so future trend now are working on smart retrievals, context-aware, intent-based, also use memory and caching for faster responses, because especially in complex models, like when you use agent, to accomplish a task, you may need to go through several iterations. So you need to remember everything that was in the past. There is a nice course that is long-term memory with LangGraph. If you are interested into learning about this, they have made an API to store previous conversations locally into like a vector store will be vectorized to speed up the retrieval process of long context. Because usually in long context, you don't want to keep the whole conversation as a text. Okay, it's long. So they convert it into a vector. Whenever there is a query, try to bring the chunks that are related to that query to augment the generation. So everything comes back to a RAG, because RAG provides a way to retrieve information pretty much fast. Okay, so I will talk about vector stores, but during the maybe 1 or 2 minutes before Salat, let me show you one of customer support service chatbot I've done for one of the companies. This is a company in Tunisia that manufacture electric vehicles, and there in Tunisia they speak either French or the Tunisian slang. So this chatbot basically it can respond to a French. I think even if I ask in question, it will respond me in French or using the same. I think it will respond also in English. So it will respond in the same language that you ask. If you ask in French, it's going to respond you also back in French. I can ask a question even in Arabic. Okay, so this, it's kind of retrieval-augmented generation, but in a very simple way. We use kind of the context. Whenever you have a question, you send all the context. The context was not very large, so I didn't need to make vectorization. But one of the ways of to do retrieval-augmented generation is what we call long context large language models. So if your context is still reasonable, you can just send it completely with every question. Okay, if it is not very long. But if you have, for example, 1,000 pages or 2,000 pages or a couple of thousands of pages, you cannot every time, in every question I could send the whole context. But here, for example, I ask, نحب نعرف أسعار السيارات. Okay, so I ask in my accent, and it's going to respond in Tunisian, here. This is a Tunisian accent. Okay, we can, yeah, it's fast. And we can make it in Saudi accent, because now we use the capabilities of language model that they have and they're able to understand different dialects. This is built in OpenAI, for example, or in Claude. Of course, some other language model may not have this capability, but when you learn this technology, you can adapt it to any context. This is an example of a customer support service that use kind of a simple RAG technique. Because now, if I ask the same question to ChatGPT, will not be able to respond accurately to this response.
RAG is extra information on information.
Yes. So now, with every question, it will send additional context along with the question that contains. So it only responds to the context that it is specified. Now, for example, if I say I want to make pizza, for example, so it can respond in a funny way. So it say أنا باش نعاونك في باكو موتر فقط. So we specify the context. It has a specific role. Okay, and I made it in a way to respond in a funny manner. Okay, بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is the continuation of the lecture on Introduction to Retrieval-Augmented Generation. I have made an overview about this technology and its different components, how it works and why it is useful. So now I'm going to talk about an important component of Retrieval-Augmented Generation, which is the vector store. I have already introduced verbally, but I want to introduce this more formally because it's important, and then in the practical side, we will work with vector stores. So what is a vector store? As already, it's a database of vectors, and this is why we call it a vector store. And we will use it to store and save all the documents that we collect, and we will save them into a vectorized manner. So we will use an embedding model to convert any text, any chunk of document, could be paragraph or more paragraphs, and we will convert every chunk of text into high dimensional vector embedding, and then we will store it into this vector store, which will represent our database of documents. And why we use this, why this is important in RAG, because it will allow to make semantic search based on the similarity between the query and the documents that we want to retrieve. So this enables dense retrieval or semantic similarity retrieval through vector similarity comparison using the cosine similarity. And we store the vectorized documents representation into the vector store database, and then having a query, we will be able to retrieve the top k similar documents or items based on the query vectors. So how this works, when you collect, for example, documents like PDF, you will extract the text, and then you will take this long text, subdivide it into different chunks, could be several paragraphs. You can divide them by a certain number of characters, or you can make kind of semantic chunking. For example, paragraph with the same meaning will be aggregated together and then put as one embedding vector. So in any way, we need to find a way on how we will subdivide the long text into chunks, and then convert these chunk or document chunks to embedding vectors, and then index them. So we use an index to store these vectors efficiently, to retrieve them quickly, and transform query also into the same vector space using the same embedding model. And finally, we retrieve the relevant documents based on the similarity search. Okay, so having a PDF, we need to, first of all, extract the text from the PDF, convert this PDF into different chunks, and then every chunk to embedding. And then we will use a vector store technology like Face or Chroma DB, or there are some others, to store these documents. And then having a query embedding, we will make the dot product or the cosine similarity across all these stored documents, and find the top 5 chunks or the top k chunks that are more relevant to the query. Of course, how this works, we already introduced this in tokenization and vector embedding. Every word can be converted to an embedding, or a whole text can be also converted to an embedding and then stored into a vector store. Okay, I already introduced this in the previous lectures, how to convert some words, capturing the semantic similarity using the cosine similarity between two vectors. You are already familiar with these diagrams. And finally, having a source of data, we will load the data, we will transform it and store it. Okay, we use, so transformation here, it means a long document will be converted into chunks, and these chunks will be converted into embedding vectors using a certain embedding model. And finally, we store them into a database. Now, having a new query, we will use a retrieve function to search using semantic similarity between the query and all the documents, and finally return the top k documents. So that looks natural, but in practice, the retrieval performance may depend on several factors, including the chunk size. This is one of the important factors. It can depend also on the type of embedding. If the embedding model is large, usually we can have better semantic similarity because we can capture more nuances into these documents. But of course, this will be at the expense of larger storage requirement and also slower execution time due to the embedding size of the vectors. So there are several popular vector store libraries, including Face by Facebook or Meta. Okay, it's fast, flexible, and open source. This is a free version that you can use. Chroma DB is also a very popular vector store library. It's a simple Python native database for large language model applications. And basically, it's going to store this Chroma DB and also Face. They will store the vectors into an SQLite database. Very simple. So if you open the SQLite database, you'll find the vector store and its corresponding document. So now if the vector store is on the top k, we will bring the context from the SQLite database and then append it to the query before sending it to the generator, which is the large language model. V8 is also a full-featured vector store with REST API. So this is cloud-based. So Chroma DB and Face, you can use them locally. V8 and Pinecone, Quadrant, these provide also cloud-based solutions. Sometimes you may need a cloud-based because if you have a huge amount of data, you put them locally, you will require high computation speed. So cloud-based solutions are also viable solutions, but this will come at a cost of storage. So the key feature of vector store is indexing, which means the way on how we can organize vector for efficient retrieval. There is the similarity search, which can use cosine similarity, L2 norm, and inner products. The meta filtering, it's retrieving by tags, finding the source of documents or also the topic of interest. Persistence, it means keeping the data stored physically into the hard drive. And scalability, it must handle millions of vectors. Okay, So building a vector store, efficient vector store software is also challenging, but now there are several available solutions. Okay, so I think no need to talk about embedding techniques. This is a lecture also that I've made for some other audience. You know what is embedding techniques. This will help to convert any document into vector space to be able to find documents based on semantic similarity.
Doctor,
Yes.
RAG gets converted into embedding, صح؟
لا الراج it means retrieval augmented generation. هذا الكونسبت العام. What we convert into embedding هم documents or chunks of the documents. Okay. المفهوم العام اسمه راج اللي هو using retrieval before generation. Okay. What we do embedding are documents. So I have a large document. I'm going to show you examples. We will subdivide it into chunks to have a certain context size. And then these chunks will be converted into an embedding model using some embedding models. We can use OpenAI embeddings like we did before. There is Sentence BERT also, Instructor XL, Cohere, Hugging Face. All of these provide different type of embedding model. But of course, the embedding model that you will use to build the vector store must be the same embedding model that we will use to make the query. Okay. So we will have hands-on notebook I can share with you, and we will see how to do this in practice. Yes.
Beginning, you said that documents or like external data can be different types, like websites or database. Does this concept also work on it, like the chunking?
You know, yeah, there is chunking, but in probably different way. Now, what I'm talking about as RAG is when you bring external documents and we vectorize them locally. نتكلم عن vector store. الآن when you do, for example, RAG through internet search, you have options. طبعا there is no vectorization. You will have an API like Tavily or a SERP API, which will allow you to search over the internet, and they will bring you documents. So you can choose, would you like to bring the raw text? So it will bring you the whole raw HTML page as a raw text, or you say, only bring me the part of the raw text that likely to respond to the solution. So these search APIs allows you to bring either response from a website or the whole raw text. طبعا whole raw text can provide more rich information, but if the context is very large, نفس الاشكال اللي عندنا في long documents. And you know, we will use an embedding model to convert any text, not only words, but any text to an embedding vector similar to this one. And this is an example on how we can create a vector database. Look, very simple. So first of all, we will here we will use OpenAI Chroma DB. It's a Python library. We will use its client, and here it has also embedding function. So we can use embedding function from Chroma DB. It also offers embedding function using OpenAI, or we can use here, like we did here, embedding function.openai embedding function. Here you provide your API key, so it's a paid service, and the name of the embedding model, text embedding 3 small. And we will create a collection which is Chroma client, which we created here, .create collection. We will give it a name, and we will give it an embedding model. That's it. So what it will do now, this collection, for example, you will provide these documents. Let's consider these are chunks of a text. This is the first chunk, this is the second one, third one, and so on. Now we can add them one by one, or just make collection.add, and we provide this list of documents all together. So it will add them one by one for every document. So these are the IDs, the indexing, and these are the documents. Collection.add will add all these documents. Every document will be one vector store, one index, and the document itself. Okay, so in the retrieval, we will find which is, okay, now result collection.get include documents and embedding. And finally, look, we can see the content of the whole vector store. Now the vector store contains the document number, the text itself, and the embedding. Okay, so here I go through, look, collection.get, I will get all the documents here, document and their embedding, and then I will print all of them. So this text, okay, correspond to document 0, and it will have an embedding of 1536, and here I print the 5 first elements of that embedding. Okay, so now I converted this text document into an embedding or a vector store. So later when you have a query, this query is going to be compared against all these vectors, and then the highest similarity score will be considered as the top K. واضح الفكرة؟ Okay.
This is without ranks.
هو هذا الآن الريتريفل part of the RAG. الريتريفل أول شيء converting the documents into a vector store, and then use the vector store to retrieve the best documents. Best documents ما معنى best documents? The highest similarity score. Now I'm going to talk, before moving to the notebook, about the chunking techniques, and we talked about chunking. So let me show you why we need chunking. So let me just make a small break on the theoretical part. Okay, before going to chunking, I would like to give you an understanding about why we cannot vectorize a whole document. Now, First of all, you need to mount the Google Drive, and this is a notebook about building a document retrieval system. And just to give you a context, so here we will be using a data set that I have collected about Al Faisal University. So the objective is to build a chatbot for Al Faisal University. And for this, I collected raw data from the internet, which contains a description about the university, the different colleges, academic programs, the address, and different other information, some name of people. You know, it's not complete, but you know, this is just provide some ground to test a chatbot with a certain context of interest. And now this is the notebook. So this is just, it will print different chunks with a size of 200. And first of all, we need to install the different dependencies like Chroma DB, LangChain, OpenAI, because we will use OpenAI here, Python.env, and also the OpenAI library. So this take a little bit of time, and we have also pip install LangChain experimental. That's another dependency that we need. So here we need to prepare our environment for building a document retrieval system. So the load.env will be used to securely load the OpenAI API key, because we will be using Gemini 4.0. And here I provided an OpenAI key for this particular lecture, but later on, if you want to use it, you might need to obtain an API key from OpenAI. And you can change OpenAI if you want with another model of your interest, like for example, Claude or Gemini or others. And then we will create a sample text, which I already mentioned to you, and we will divide this text into different chunks. So let's first import these libraries. Chroma DB, it's for the vector store. LangChain text splitter. So we will use here character text splitter. I'm going to show you other techniques for splitting the text. Character text splitter, it will split the text based on certain number of characters. لا مش tokenization. Tokenization تقسم الكلمة. الchunking يقسم الdocument. Okay, so it's different. Now I'm loading the OpenAI key, put it in the environment variable.
Does the chunking affect accuracy?
Yes, a lot, and I'm going to show you the impact. Okay, so, and this is the text that we loaded. It's alfaisal.txt, the same text that I have shown to you, which contains some information about Al Faisal University. The next step, we will initialize the vector store database. In our case, we are using Chroma DB, but basically if you use Face or other technology, the principle is the same, okay? Because this vector store is going to convert documents from text into vectors and then store them into the vector store. So let's make a first attempt here. We will start with a common mistake, which try to embed a long document without chunking. By the way, the document that I have now is not very long, but I'm going to emulate a long document and show you what happens. So this section demonstrates why we can't simply feed large text directly into our embedding model. Because an embedding model, like a large language model, it has a context size. So let's look at this method. It's a method getEmbedding, which takes a model with a certain size, okay, with a certain name. So here, this model has 1,583 elements, and we will provide the text, and finally it will provide as an embedding vector. So let me take this text, and I'm going to append this text multiple times just to have a very long text. Yeah, I'm going to duplicate the same text several times because this text is not very long. I just want to emulate a long text. Look now. Yeah, of course. I mean, you should not have any duplicate. Now, I'm making duplications just to increase the size. And now this is a long context document. And now I try to get the embedding of this text to convert. But it's saying to me here that this model maximum context length is 8,192 tokens. Even an embedding model is like a large language model. It has a context window. It cannot accept more than 8,192 tokens. And I requested like 31,000 tokens. So if you have a long context, you cannot make an embedding. So in this case, what's the solution? I need to subdivide this text into chunks, into smaller documents. Okay, and this is what we call chunking in the Retrieval-Augmented Generation, because we cannot embed the whole context in a single embedding vector. It's not going to be aslan useful, because we want to have specific semantic information into different chunks to only load the chunks of interest that are relevant to the query. Okay, so we need to guarantee the retrieval relevance by considering smaller amount of information into a chunk. But now you can say, so there is a trade-off. If we take every chunk is only one word, will this make sense? No. So the chunking size, it's a hyperparameter. Okay, the number of characters that we need to embed. Now let me take only the text to embed, so I can take the whole text into and make the embedding because it's not long. Okay, so now the whole text that I have in hand, it's converted to one embedding vector. Now it's possible to store this, but it doesn't make any sense. I mean, every time I'm going to make a relevance score, is going to only make it with only embedding vector. So, and if we look at this document, which I have shown to you here, it contains different type of information. Look at this document. Now this information is related to introduction. So now if I have a question that is, what is Al Faisal University? I could be more interested into this part. And you know, all of this present what is Al Faisal University, but probably some of the information, maybe I don't need to talk about the library and facilities into this question. But if I ask, what are the facilities of Al Faisal University, I could be more interested into having a look into this part of the text. Now the question, I have a long, you know, you can imagine that this text is even longer. And it could be not organized. Okay, because now, one of the ways is just to take, to divide this document into chunks of 100 characters. Let's say 100 character will take the following first chunk. These are first 100 characters. Okay, and let's look what happens if I choose only 100 character in here, the first 100 characters. Text. So this could be a chunk of information, and that corresponds this embedding vector and the following sentence. Okay, when you split your document into fixed size chunks, so you may have something similar to this one. It presents a context, but it's truncated. Voila. So there is a way on how to alleviate the issue, is to make a kind what we call an overlap. Now imagine I would like to take the next 100 characters. I can do the following, from 100 to 200. And this, look, is the premium, private, non-profit, institution. Look, it comes into the institution and subdivided into two. You know, here I will lose a context. There is a word, I'm going to lose it. And also probably I would prefer to put maybe these two sentences into one context, or at least not to truncate. Okay, one of the ways is to make an overlap. For example, instead of starting the second chunk from 100, I can start it from 80. So in this case, some part of the information of the first chunk will be appended to the information of the second chunk. طبعا the overlap, it's also specified in number of characters. You may want to increase it. For example, من 50 يصبح إلى 150. So this is another one. Okay, so it helps recover some of the information of previous context, and في الأخير we can have the comment for one question, what is Al Faisal University? If I bring this context and this context, the LLM can know that, you know, there are some overlap here, so probably it's part of the same sentence. But in the first case, it looks like completely disjoint, so could be make it a little bit harder for the LLM to find an association. Yes. So in this case, no, you can put, I mean, you can put any number. So these are hyperparameters. Okay. Usually you can put, for example, 512. Okay. And I can put an overlap of, I don't know, maybe 256 or 100. You can start from 400 to 912 as another chunk. So here I added 100 character from the previous one. Okay, look, all this character comes from the previous one, and this is a little bit longer. So now, what is the chunk size? 512, more or less, depend on your large language models, based on the type of your query. It's not, there is no one size fits all. Okay, this is not probably the best. We don't know what is the best number of characters to put. But you know, the advantage of the fixed character chunking is that you'll have all the chunks having the same size. So you can control over the size of the documents. Now, let me come back to this presentation and talk more about chunking and chunking techniques. I gave you some flavor about the importance of chunking. And now having a query, okay, we'll calculate the embedding of that query, and then an external document, which is large, will be divided into several chunks, and these chunks will be stored into a vector store or a vector database. So this chunk will be converted to embedding number 1, which is one vector. This chunk converted to embedding number 2, this chunk converted into embedding number 3. And when having a query from the user, will also convert it to an embedding, and we will do the dot product across all these embedding vectors. And finally, we will bring the top K documents with the highest similarity score. And this will represent our context that we will send to the LLM for generation. So chunking divide large documents into smaller segments to enable efficient processing in NLP tasks. They are important because they allow to enhance the processing. When we have smaller chunks, this will allow the model to handle information more effectively, especially for very long documents. It also contributes to improve the retrieval, because in RAG systems, the chunking enables precise matching between the query and relevant documents. And when the documents are small, so the similarity score will be kind of higher when يكون very long documents, because the noise will be less. And also we need to keep the context preservation. Proper chunking maintains semantic integrity. So we should not only care about having a fixed number of characters, but I like to maintain the semantic integrity of the chunks. For example, I would like to make the chunking with proper paragraphs, okay, that have similar meaning. ما نحبش نجي مثلا تخيل مثلا you want to make retrieval augmented generation على الحديث. ما نحبش نجي في نصف الحديث مثلا ناخذ منه جزء وبعد يقسم وبعد ناخذ جزء من مكان ثاني، ما عادش يحمل نفس المعنى. فانت الان لما تبحث على حديث معين على حسب سؤال، يمكن يجيبك في التشانك هذا، ممكن يجيبك في التشانك هذا، ممكن الجزء اللي عنده علاقه بالسؤال يجي في تشانك اللي فيه جزء من الحديث غير مكتمل مثلا. اوكي، ف we need to maintain the semantic integrity of the documents. Okay, so that to ensure that each chunk contain coherent information، مش معلومات من هنا ومعلومات من هنا. Okay, so chunking techniques, we have text-based splitting, and we specify a certain number of characters with an overlap, as already mentioned. There is what we call the recursive character splitting. It applies a hierarchy of separators. Okay, paragraphs to sentence and to word to text split. So if the first split results in large chunks, it recursively split into smaller units. مثلا الآن I want to take a paragraph by paragraph. فإذا الباراجراف كبير جدا, recursive is going to chunk this paragraph into sub chunks as well. So this will help to maintain the semantic coherence while ensuring the chunk size limit. لأن بعض الأحيان you don't have control over the length of paragraphs. بعض الباراجرافز يمكن تحصلها 1000 كاركتر، بعض الباراجرافز 10000 كاركتر. ممكن النص ما كانش منظم بطريقة أن الباراجرافز يكون عندهم balanced size. So the recursive text splitting is an advanced character splitting that ensure both the semantic coherence by chunking with respect to paragraphs, and if the paragraph is very large, so it's going to recursively chunk it into smaller size. There are splitters based on HTML tags, so it can help, for example, split the HTML documents based on H1 or H2 based on the sections or subsections or paragraphs, depending on the logical structure that you want to have your chunks. And there is also code splitter. هذا كل موجودين في LangChain. They are specialized for handling programming code files, split files into meaningful units such as functions, classes, or modules. Okay, so I'm going to leave this presentation now to focus more, but here I provided to you more theoretical background with some LangChain examples about the different chunking techniques that you can use for subdividing a document into subdocuments. Okay, going back to our chatbot. So now I think you have understood the need and the requirement for chunking the documents. Let's move forward. So here we will initialize OpenAI embedding model to work with Chroma DB. So Chroma DB, it can use an embedding model. We can use either OpenAI embedding or other type of embedding. You can bring Hugging Face or an embedding model. So the choice of the embedding model may depend on the type of your data. مثلا لو عندك مثلا باللغة العربية في other embedding model يكونوا أفضل، لأن الembedding model مش يأثر في السيرش. مثلا لما نستعمل OpenAI embedding small, the quality will be lower than if I have OpenAI embedding large. But of course, with large, we come with additional cost in terms of storage, in terms of memory, and in terms of computation. So all of this is trial and error, and you will choose something that provides the best trade-off between resource consumption and also efficiency and reliability. Okay, I'm going to use text embedding 3 large because my data is not very huge, and the collection name. I'm going to create a collection. So when you create a vector store in Chroma DB, you need to create a name of a collection. So here I call it no chunks because I'm going to just create a collection that contains the whole document. Just to make sure that you will not create a collection that is created, so you can safely, when you will create a collection from scratch, you can safely delete a collection possibly with the same name and created another one. Okay, so look now, because imagine that I don't do that. Collection no chunk already exists. موجودة عندي. Okay, so now if I do the following, it deletes the old collection and create a new one. So this collection is created using this collection name and with an OpenAI embedding, but still it's empty, doesn't have any anything inside. Let me check here if I can see it in the folder, my drive. Okay, still it's created in the memory, but not in. Okay, and now I'm going to raise, I'm going to add the, so yeah, I already mentioned this. This is for a long context to show that there could be an error. Okay, this is going to work, no problem. And now we'll use text chunking to solve the token limit problem that I have already introduced previously. Okay, so this example was meant to add a long context. Now, if I want to make it work, okay, that it doesn't allow, I'm going to make first small to have a smaller context window. I'm going to delete the old collection and let me add a long context here. So if I don't chunk this long context, it will result into the error that I have previously shown. Now, to avoid the issue, we need to do text chunking, okay, which means splitting the large document into a small document. So let me take this one and I'm going to call it large document. Large or text equal, because everything I'm going to use it below, it's the text. So let's consider that text is the large document now. And now I'm going to use from LangChain text splitter, I'm going to use character text splitter. And this is going to subdivide this large document into chunks of maximum size 1000 and an overlap of 200. Now let's do the following. And it's done. Now our large context is split into smaller chunks. Look now, I have 1, 2, 3, 4, 5, 6, 7. This creates a chunk of size 4763, which is longer than the specified. But why it is longer? So it has created some chunks which are longer. That's there's an explanation of the separator. Because of the separator here. Yeah, you know, here in the character text, it will be focusing on also the separator. It's true that we have specified the chunk size, but since we have specified the separator, is going to consider the separator as the criteria to subdivide the chunks. I didn't use here a recursive chunk size. Look, in my original text, I didn't have any separator /n/n. It's only 1/n. So it couldn't find. So it took the whole text as one context. It didn't make any split. Let me change the separator. So here I'm going to consider that every paragraph will be a chunk. Now this is every paragraph will be a chunk. Look now, I didn't have the error. واضح؟ لأنه it will take this paragraph, but also it will take mission and vision as a paragraph. Okay, because it has used the /n, the carriage return, as a separator. So this is a little bit tricky because we intuitively think that it's gonna make the chunk size, but now if we look at our chunks, we have the separator that will be used to tell the text splitter to try breaking the text at paragraph breaks, the double new line first, and sometimes this creates chunks larger than our specified chunk size 1000. Now, if I put this one as 5000 and make it /n/n, let me check. A warning. It will create it, but it will make a warning. Look now, before I had some of the chunks, a warning even for 4000 chunks. Now, if I make it here 8000, no warning. But the context will be very, very large. So let me just delete this one, taking again the text and making 1000 here. Now, if I divide only in paragraphs, that also, but let's make it like this. Look, now all of these are warnings. Okay. لأنه التكست سبليتر يحافظ على semantic coherence اللي هي أولى من number of characters. فأنا قلت له semantic coherence موجودة على السبريتر هذا. فلذلك الآن in practice في semantic chunker اللي يستعمل large language model to understand what paragraphs are similar يشتغل. لكن بعض الأحيان اللي وجدته جيد أنا الآن بعد كثير من الأعمال أنه you put manually separator between paragraphs that you think are coherent. مثلا الآن أنا نحب نخلي هذا كله مع بعض. نجي نعمل سبيشال كاركتر مثلا. إذا الدوكيمنت has a reasonable length you can do it. يعني أنا I found for example in some of the data set they do this explicitly, and for example if I make separators نجي لهنا مثلا I will make this separator. Okay, I will consider this as a paragraph, and then vision and mission, that's another one. So I can choose myself. Okay, and look now, this is colleges and academic. فالآن ممكن لو نعتبر هذا الكل جزء لا يتجزأ. خاطر الآن لو فرضنا لو نجي كل كلية نخليها وحدها، لو نسأل what are all the colleges ممكن ما يحصلش الشانك اللي فيه كل الدوكيومنتس. أو مثلا تقول له أعطيني توب 3 يجيب لك 3 colleges ويترك لك البقية. مثلا this one it could be better that I put all the colleges together. Yes, we will see if this one, for example, I don't think that is going to be more than maybe 1,000 token or something like this. Let's make this approach and check it. Research and innovation. Okay, that could be another paragraph. And student information facilities, information technology, financial aid for the student. Okay, so you can choose. Now contact information, obviously I can make it by itself. Conclusion here. Now if I want to take this one to another one, to the top, probably as part of the description of Al Faisal University, and that's another description about also the distinguished leaders of the scholars. I can try to put all of these together. Okay, now I have kind of a logical subdivision of my document. This is feasible, as already mentioned, in small documents. Well, you can automate. I mean, if you extract data from website, you can make a script that extract, for example, part of the data and then put it into text and put a separator. You know, every use case will have its own solution. Okay, but we can automate in several cases the way on how we can annotate the data for better efficiency later on. Which one? As I mentioned to you, if you cannot do it manually, you need to find another way. Well, at the end, you need to find a proper way for efficient similarity. ممكن إذا كان database is very large تستعمل semantic chunking. Semantic chunking يستعمل large language model to automatically divide the document into chunks. أي لكن it's costly يعني بتستعمل LLM اللي هو باش يقوم بعملية التقسيم. ياخذ النص ويقوم بعملية التقسيم. Okay. So it will do the similar things that what I have done, but using a large language model. Okay. باش يقسم بطريقة أفضل. It depends, as already mentioned. Now, for example, this with separator. Usually, when you have large data set and you cannot do proper segmentation, you will use a semantic similarity search, semantic chunking. Okay, semantic chunking يستعمل large language model يقرأ يقول هذا باراجراف وحده، هذا باراجراف وحده، هذا باراجراف وحده، يقسمهم خليهم chunks and then put it into the vector store. Okay. لكن أنا جربت في بعض الأحيان يعني depend on the language model, maybe sometimes it can provide misleading chunking. Yeah, it's not always efficient. Yeah. Okay, let's resume now. So I'm going to continue. So we have now our text. If I load, okay, now if I continue this one, let me make just one separator. I'm going to do that with this splitter /n. And later on, let's see what will happen on the query related to the relevant document related to the query. Okay. alfaisal.txt. This is Al Faisal University and MAI554. Okay, now it's the same text. And now I'm going to use the second method, which is a recursive text splitter. Look at the recursive text splitter now, it's better. I can specify two types of separators. And we can look at the chunks now. Look at the chunks. So this is chunk 1. This is chunk 2. How many chunks we have? Created 10 chunks. So these are the chunks. This is the first one. This is the second one. This is using character text splitter and it's recursive. شفت الآن هذا أذكى من اللي قبله. حاول يحافظ على الطول وأيضا على السيمانتك سيميلاريتي. فهنا قسمه as paragraphs. أوكي لكن التقسيم الآن شوف الآن جاب هذا الانترودكشن to the colleges في previous context في الكونتكست of overview about Al Faisal University. Okay, and then it made every context every college as a separate context. It's not bad. It's not bad. I mean, it's much better than the previous one. Campus and location, okay, it's already in one chunk with the contact information. Okay, so for splitting with no separator, if I remove the separator only using the chunk size, it will do it also. Now we will have exact chunk size, and I didn't specify the separator. So I'm showing you the behavior of the chunking techniques under different conditions. Look now, I didn't specify any separator. لو نعمل separator معين يتغير الchunking. Okay, but if I don't specify a separator, so it will use only the strict chunking size. Okay, with the overlap. الآن هذه مثلا تنتهي Bachelor of Business Administration. Okay, and there is an overlap. Okay, College of Business, Bachelor of Business Administration. So all this text 200 is just an overlap between the different contexts. Okay, these are the chunks that we will have. وعندنا أيضا semantic chunker. هذا it will use semantic information in order to perform the chunking. ولذلك semantic chunker we will provide it an embedding model. So it's going to chunk based on using an embedding model, capturing the semantic similarity. So it takes more time to make the chunking. And look now how many chunks it resulted. I can make print the length of chunks. 6. If I change it to small, it made also 6. Look, this is a chunk. It considers all of this as one semantically coherent paragraph. And it's not bad because, you know, consider everything is an introduction about Al-Faisal. This is a library plus contact information. And this chunk is about the president, and this chunk is some board members. Not perfect, I mean, but still it makes some sense. I don't know with the large what will be the chunking subdivisions. Look now, here the chunking is a bit different. 6 chunks but in different way. هذا الكونتكست هذا كامل. Okay, so you can observe the semantic chunking. Try to make the best possible. The embedding model will play a big impact on the resulting chunking techniques. طبعا in real project it's a matter of trying, you know. You cannot say that one method is better. If you can control your chunks in advance, do it. Otherwise, try semantic chunker. And in some projects, semantic chunker was the best option. In some other, recursive chunker was best option. Depend on the scope of your database, how your database is organized. And the most important thing, try to come up with the best organization of your documents that maximize the retrieval quality. Okay. Now we have understood embedding, chunking. Now let's look how to build a vector database and do a retrieval augmented generation. وللأسف الوقت قريب يخلص. I think about completing this tomorrow also. لكن خلينا نكمل على الأقل الساعة 8 لأن بدأنا متأخر نوعا ما. Okay. So let's create a vector database. I delete so I'm going to call this Al-Faisal collection. And let's do it. Collection. I want Al-Faisal collection. Okay. And then I will add all the chunks. Okay, الchunks اللي عملناهم هم semantic، لكن أنا أظن إنه recursive are better, right? خلينا نجربه. We can try any لأنه بعدين مش نشوفوا their impact on the quality of the retrieval. So I will do again this one, delete, and this is our collection. Okay, we have a collection that is called Al-Faisal collection. Now, this collection contains a vector store with all the vectors and their corresponding text. Now, create a vector database. Now, we created this into several steps. This method just gather all the steps together into a method to finally get a collection. But we already did this. And now, after creating the collection will be stored into the hard drive. So we need to load it into the memory. Now, there is a function. This is a function that will load a vector database. Okay, so how to load the database? We create an object Chroma client, and then we call Chroma DB persistent client path equal persistent path. What is our path here? I called it Chroma DB because I think I saved it here. Okay, I will create. Now, this one is not saved. It's still in the memory. I need to make a persistent directory here. So look at this one, persistent directory. Okay, when we create it, we need to specify the path to the directory where the vector store will be stored, and then to load we need to use the same name of the vector store. So let me just do it. Create a vector database, chunks, my Chroma DB, or I can call it, let me call it iFaisal DB here. And here I loaded the collection. Okay, let me show the collection content. So this is a method that goes through all the documents and show the collection content. Let's try run it. Okay, now the first document contains this one, Al Faisal University, then we have College of Business. These are the different chunks that we have. And now let's make the retrieval. احنا قلنا الراج فيه retrieval pagination. And we can separate the retrieval الآن. الكروما دي بي فيها collection.query. Okay, what is the contact information of Al Faisal University? لو نشوف الchunks الآن we have 10 documents. One of them اللي موجود فيه. Okay, let's see whether we are able to retrieve the best document. Okay, so if you look now, I selected 2 results among the 10. Look, this is the first document retrieved. وفيه البيانات على الكونتاكت فنجح الفكرة الآن. اوكي، السكند دوكيمنت هذا أقرب شيء. شوف السيميلاريتي سكور. الديستانسز 0.4 and 0.68. يقول قائل لماذا المفروض هذا الدوكيمنت 0 الدوكيمنت 5 أظن أقرب. اوكي، what is the contact؟ يس هنا 0.68 لأنه عندنا كلمة الفيصل يونيفرسيتي وهنا في كونتاكت. اوكي، فحسب الريليفنس سكور ممكن يكون هذا أقرب، لكن هو في الحقيقة هذا أقرب، ولذلك شفت الآن الدوكيمنت الأفضل بعض الأحيان ما يعطيش the best relevance score. هذاك علاش الآن when we work with RAG في بعض التكنيكس اللي تسميها ري رانكينج. نرسل الكويري ونريتريف الدوكيمنتس ونجيب ال LLM we ask the LLM re-rank the scores based on the relevance. We don't trust semantic similarity always لأنه الآن الكونتكست هذا فيه noise and this context contain noise. هو باش يشوف هوني فيصل يونيفرسيتي هوني متكرر فيصل يونيفرسيتي several times فيقول لك this context is likely contains the semantic information that I need. Okay, لكن with a smart LLM it will be able to understand that probably this one is more relevant, so it will make another re-ranking. They are trained to give scores based on the relevance. Okay, and so let me just remove this one, remove this one, remove this one. Use the same text. واضحة الفكرة الآن؟ now when we have a RAG pipeline, so all the RAG will do is extract the most relevant documents and send it with the query to the LLM. Verify the collection. Okay, let me skip. Okay, now this is to create a RAG pipeline. So we're almost done now. This is the RAG pipeline. We will provide the collection and we will provide a database of the collection and using LangChain creating the embedding models. So I used the small here. Make sure to use the same embedding, okay, that you created database. I'm going to load, here we have Al Faisal collection. Okay, so this is the name of the file where we store the database. And this is the name of the collection that is inside the file, Al Faisal collection. And now I will use an LLM, large language. This is my generator. Look now, this is my retriever, and this is my generator. Okay, I will use GPT-4 Omni, and there is a system prompt for Retrieval-Augmented Generation. I can write my own prompt. I can make prompt equal use مثلا UR. I can give it a context and system prompt and blah 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 things, but I'm going to use just the system prompt. Let me just print it. Print prompt, and here it's prompt. And this is the RAG pipeline. Look at the RAG pipeline. It contains a context. This is my question. So it will first retrieve the context based on the question, and then using the prompt, we'll send it to the LLM, and finally it will present it as a string. And I don't know if you have made LangChain before, whether we have taken any course about LangChain. But anyway, don't worry about this. This is the way on LangChain on how to build a Retrieval-Augmented Generation. And what is the issue here? Collection, mass collection does not exist. I don't have mass. Okay. So yesterday I have already introduced the concept of retrieval. I think we finished with this. So I just fixed the configuration. Just let me remind you what we've done. So we created a collection from a vectorized document that we collected about Al Faisal universities. This is the context. For example, now after making a collection of vectorized documents, we can use collection.query. Alaikum assalam wa rahmatullah. Collection.query to find the relevant documents, okay, from the vectorized database. So these are the documents. I think we have 6 documents in total. And now, for example, if I ask what is the contact number of Al Faisal University, so in this case, we will be able to find the 2 most relevant document that contains this information based on the embedding that we have done. So this is a semantic embedding. Let me just roll it back to instead of semantic chunker, I'm going to make the recursive or text splitter chunker. Okay, let me just the recursive, this one. Okay. So let's go again to the query. Where is the query? Yes, this one. So at the end we will have the list of documents, and that will contain the contact number. Okay, you can see now this is a document here, and it contains the contact number. We did this yesterday. Now I'm gonna load this again, and these are some utility functions. For example, this will verify which collection we have loaded. This will allow to load the collection and send a query. Just I put some instruction into a function to make it easier. And now we stopped at this stage to create a RAG pipeline. So what is a RAG? If you remember from yesterday lecture. So basically in RAG we have two main components, the retrieval components and the LLM. So the retrieval will execute a retrieve function over vectorized documents to extract the most relevant documents to a query and send everything to the large language model to generate back a response to the end user. This is what we're going to do right now. Okay, look at the structure of the RAG pipeline. So first of all, I define my retrieval, and the retrieval we define it just using a vector store. So later on we will take this vector store and we use the LangChain function that is called as retriever. So this means it's going to consider a retrieval process or function that will be executed. So usually these are functions that are stuck one after the other in a pipeline. This is why we call it the RAG pipeline. So first of all, we call the retrieval is going to return documents. So format documents is going to convert the objects or the list of documents into a string. So this is another function. And the question is the question that we have provided as an input. So all of this will be provided as an input to the prompt. Look at the prompt. The prompt is basically is defined as a string, and it has two placeholders. One placeholder for the context, which will contain the value that is generated by the retrieval. And the second placeholder is for the question, which will be the input to the RAG pipeline that we will take it from the invoke method that we will call later. Okay, so the first part, create a retrieval through a vector store. The second part, we create the generator, which is the large language model that will be used to generate the data. Instead of having a response like this, you would like to have, now imagine that you ask the question and you get this response. It's annoying, you know, you want just a clear response to your question. You don't want all this information, but this information will be used by the large language model in order to find the correct answer to the question. So this is now the output of this will be the input of the prompt in a LangChain RAG retrieval, and then the prompt will go as an input to the LLM. This is the way how it is defined in LangChain. I really recommend you to take some LangChain courses if you didn't do that in the past, because this is the most popular framework to build large language model and generative AI applications. So at the end, this method is going to return a RAG chain. And in LangChain, every LLM or RAG chain, we use the method .invoke, okay, to send a request to the large language model. Now what will happen? I'm going again to have the collection, the same collection that we get before, and I will create the RAG pipeline. Now I have the RAG chain that will take a question, go to the retrieval, provide the context, send it to the LLM, and generate a response. So all of this is just inside the black box .invoke. Look now, let me ask, what is the contact information of Al Faisal University? Now this information, I know it's presented, it's provided in the documents. Okay, look, it's nice. Now this is a chatbot. Now we made a question answering system, okay, where if I ask another question, okay, who is the president? This could be confusing a little bit, and I will tell you why, of the university. Oh, okay, it makes it correctly. Because why? Now, if for example I take this and I will make a query like I did here, we can have several presidents here, especially because we have the board. Look. Now look at these two documents. It doesn't have the name of the president because there are many presidents. Look, okay, now it's here, but there are some other presidents like associate vice president of research. So in one of the trials that I have done, it was not able to find the answer because now imagine that I took only one response, or the most the top response, okay, the top one response, which is this one. It did not return the name of the president. It was considered as the second relevant document. You see what I mean? So now it's a problem of chunking. Okay, again, it's a problem of chunking. So maybe one of the best ways to put all these boards together into one chunk, because if you put them into different chunks, so it can find a chunk that contains some keywords and then could be confused. You know, so chunking plays an important role in the relevance of and the accuracy of the response. Let me try other questions. So now I made a prompt here that if the answer is not available in the context, don't say it's out of my scope. Now, for example, if I ask about who is the president of King Saud University, look, now it says, so we can remove hallucination. Now, if I change the prompt, let's try what happens. The context does not provide information of present. Yeah, it only mentions faculty associated with the university. That's good, not bad. Okay, if okay, so you can see with RAG we can reduce hallucinations because we provided very specific context about this. Now we can ask, for example, tell me more about Al Faisal University. Now it's crafting a long response. It's taking a little bit of time. Okay, so it brings a lot of context and then it has the ability to draft it and summarize it. Okay, this is nice, and then you can apply it to any kind of context. Bring your data, vectorize it, make the LangChain RAG pipeline, and that's pretty much it. Now, in order to reduce maybe the latency, I don't know whether it's going to work like this. Just let me check if we can stream the response. There is a way on how we can. I think I need to make a invoke. Okay. I want to try a streaming example, but I need to do some more configuration anyway. Streaming is equal to false. Because one of the ways to avoid delays is to stream the tokens one by one instead of waiting for all the text to be written. Okay, and you can send many questions as a batch. So for example, here I define questions. I just made a for loop to ask many questions one after the other. Okay, so what is your vision? Now it brought the vision of Al Faisal University. Tell me about your university. Is going also to extract useful information. Al Faisal comprises 6 colleges, which is true, and it provides these colleges in different programs. Who is the president? Was able to find it. And how can I enroll in data science? There is no program about data science, at least in the context I provided. So it apologized. What are the available programs? Was able to bring the colleges. Okay, so this is the concept of making a chatbot. No, yeah, it depends on the number of retrieved documents. Look, now if you want to go a little bit into more details, we can control the number of documents returned. Now, probably I need to go into the documentation. Maybe there are some more control parameters, like for example, how many. Look, you can specify the search type. There are different parameters in the as a retriever. Let me check if I can go to the Python documentation API reference. Python API. Search type. You can also specify the search type, whether similarity score threshold. MMR, it's another one. It's the maximal marginal relevance search. It's another metric. So this one uses cosine similarity. And these parameters may affect the documents or the type of documents that could be found. Look now, you can specify the score threshold. Okay, below 0.5, it will not make it. You can specify the top K, and this is what I want to make. Look now, if I make top K equal to 1, search arguments. So maybe some of the responses could not be answered, but let me just try this. Create the RAG pipeline. Top K, yes. How many documents we return in each answer? If I make top 5, it will return the top 5 documents. Okay, so it's a hyperparameter. Now this is the retrieval. I can make only 1 document. Look now, if I create this and I say who is the president of the university, sorry, it's out of my scope because it was not in the top document, first document. Now, one of the way to control this, I can make k equal to 2 now. Okay, so you can say, okay, let me have a long context. That's good. Could have more quality. Sometimes it can have noise, but now, if you work into the industry and you want to sell this product, OpenAI charge you per token. So in this case, imagine that you send a long text, a query, for example, of 00, for example, 10 minus 4, it can become 10 minus 2. And with the scale, you can multiply your charges by 100 or 1,000. Okay, so sometimes it's critical to make the right balance on how long the context should be to be provided. Now, if I make k equal to 2 here, it will be able to respond. Okay, so this is a hyperparameter. It's something like trial and error to try to find the best balance depending on your data set, the chunking characteristics. So you have seen now chunking plays an important role. Now the second chunk was more relevant. So some of the techniques could be, for example, re-ranking. If we use a re-ranking technique, maybe it will put the document that contains the name of president on the top and then the other documents just below. And now when I use k equal to 1, it could lead to correct answers. And there are several hyperparameters here. There is a default value, I think 3, or you need to see the documentation about this. Now you can play with other arguments like the score threshold, the search type score threshold. Okay, let me just put this here. Okay, just show you the basics and then you can play with this. And I recommend you to build your own project. Okay, because this is how you're gonna learn. And there is not only this way to create a RAG pipeline. LangChain provides different alternatives. It's a rich language. So let me. And I think this retriever, look, I think we can put them into the query. What is the query? Does this work? I don't think. No, this is not part of the invoke method. Okay, just want to try whether it could be working. To use what? Yeah, there are many re-ranking techniques. They are usually trained models, and some of them are based on LLMs. Yes, there are so many re-ranking techniques. So maybe I will do an extension of this one if you want to learn more about optimizing. So we can make a lecture on optimizing the performance of RAG models, and also I will do a lecture on how to evaluate the performance of RAG models. Okay, so look now, I put a threshold of 0.5, but it says this is out of my scope. And for example, if I make it 0.1, it's fine. You see, you have some parameters, you tune them. So you say, I would accept results with less confidence. Now, if you want to increase the confidence to the maximum, you may end up of not having an answer. يبدأ شخص متشكك في كل شيء ما يحبش يجاوب إلا متأكد ولا يجاوب to the best. So you put something, depends 0.3 or something that would work in most of your examples. Even 0.3 didn't work لأنه لما يكون الchunk size كبير يمكن relevance score يكون أصغر. Okay, so you need to find the right balance. وممكن if we change the similarity score threshold to another one, you could have a different behavior. Okay, so using this, we can also generate different answers based on this. Look, what is your vision? Couldn't find it because of the relevance threshold 0.2. Now this is more restrictive. So we can put the default values. Okay. Now, if you are knowledgeable on how to build a fast API, like REST API and so on, you can put this RAG pipeline in under a REST API endpoint, like post request, and then you can develop a web application through which you can send a question, receive a response, and visualize it, as the example that I have shown to you yesterday. So this is basically what is in the background. Voila. Okay.